Okay, hi everyone, thanks for waiting through the technical difficulties. So today I'm talking about neural networks. So this is the presentation that I gave at our Women's Day Tech breakfast event a couple of weeks ago. I thought I would be giving this presentation at 2, so I didn't really have time to adjust this for a more technical audience. So this is going to be a very high level sort of quick look into neural networks and how to use them in practice. Not quite the hello world of neural networks, but maybe the to-do list app of neural networks. So if you're already familiar with machine learning neural networks, probably nothing new for you, but then you can maybe ask hard questions or something. And again, this was originally intended for a very non-technical audience, so apologies if I go into explain like this is a Python interpreter. I know you know it, but the original audience didn't. So for the presentation, I programmed what I called CatNip, the cat neural image processor, a neural network classifier that recognizes whether there is a cat or a sheep in an image. So the original motivation was to sort of, well, because there's a lot of AI in the news, there's a lot of deep learning in the news, but the news, they're often very abstract, they're very high level. There's a lot of talk about future risks and future possibilities, but little talk about how these things actually work. So I just wanted to run the audience through a simple example of how to implement a neural network and how it can be used in practice. Neural networks, they are a family of machine learning algorithms. There are many kinds. We'll be going through a couple of examples later on. And originally neural networks were sort of inspired by how neurons connect in animal brains, but these artificial neural networks that we're going to use, they don't really have anything to do with biology. They just borrow terminology from there. Tech stack today, we're using Python and a library called Keras, which is a very high-level deep learning library. It can be run on top of several different sort of lower level machine learning libraries. We're using TensorFlow, which is a well-known Google library for machine learning. In the best tradition of data science, it's all going to be in one long Python script that we're just going to be copy-pasting stuff from and to. Okay, so our application today is image classification. And there are, of course, well, it's a very common type of AI problem. There are many cases where we want to separate images into different groups, or we want to automatically label them with some labels. For example, there's optical character recognition, so reading text from images or scanned photos or whatever. So we need to recognize what letters are there in the photo. There's facial recognition, who's the person in this picture. There's a lot of medical applications, like here's a tissue sample, a microscope image of a tissue sample. Does the patient have cancer or no? And so on. Or then our application, which is it a cat or is it a sheep? Here on the left, a cat. On the right, a container ship. Yeah, yeah, you knew it. I mean, humans are really good at recognizing objects in images and objects in real life. I mean, you all knew it. I didn't have to tell you which one is which. But of course, this is not an easy task to code into an algorithm. Like, how do we know what makes an image a cat image and what makes it a sheep image? Like cats have ears and eyes, and ships have, I don't know, sharp angles. But how do you code that into like a big if-else tree? It's very hard to do. Here is an example computer representation of a color image. So what we've got is 3 matrices, one for the red, green, and blue channels in the image, and one number corresponds to 1 pixel in the image. So for each pixel we have 3 values, red, green, and blue value, and then how do we know is this a cat or a sheep? These are actually just numbers I made up, but you don't know that. It's very hard to say. Like, if we wanted to make an algorithm that recognizes the catness or sheepness, like, okay, if the blue value in the lower right corner is below 50, and then it doesn't really work. It has been tried for decades, but it's very hard to do, and it doesn't really work. So what we need is an algorithm that will somehow itself learn the rules of what makes a cat image and what makes a sheep image, so that we don't have to manually write those rules. So we're going to use machine learning, as you already knew. And to learn the rules of catness and sheepness, we're first going to need some training data. So we need examples for which we know the label. So a bunch of cat images and a bunch of sheep images in this case. And then we need an algorithm that can somehow use the information in our training data to adapt itself for the task that we are giving it, which is now the image classification task. And then, given the data and the basic structure of the algorithm, we somehow need to fit the model for that particular task. And when we've done that, we can then use the model to predict labels for images where we don't know the label. This is called classification officially. It's not the only possible goal of a machine learning system, but it's a common one. It's an easily understood one, so that's why I chose it as an example here. So, step one, get some data. So we need images of cats and sheep. And getting the data is actually often like the most difficult step in implementing a machine learning system. Because, for example, here we're going to need images where we know the label. So someone has to do that manually. Here, I didn't label images myself. I used the CIFAR 10 dataset, which is a sort of well-known teaching and research dataset from the University of Toronto, I think. It's got 60,000 images, very small ones, 32 times 32 pixels. They come in 10 classes. We're only going to use the sheep and cat images. And someone, probably some underpaid research assistant, has helpfully already labeled all these 60,000 images for us. So, okay, there are 60,000 images, and they are divided into training data and test data. So 50,000 images of training data, and 10,000 images in test data set. And what is training data and what's test data? This is something that I skipped in my original presentation, but since we've got half an hour more, I can quickly tell you that. So the data that we're going to use, it has sort of two kinds of variation. There's the variation that we're interested in. It's the information that tells whether this is a cat or a sheep. And then there's information that's sort of, there's variation that's, how would I say it, not related to the class label. It could be sampling bias. Maybe we got a lot more black cats than white cats. It could be mislabels. Maybe our research assistant was very tired and labeled accidentally sheep as cats or so on. So there's some kind of variation that we don't want to model. So when we are fitting our algorithm, we are doing that using our training data, but then we're actually interested in how well it does on data it hasn't seen before. So when we're assessing how well our newly trained neural network is doing, we're going to have to use examples that we did not use in learning the model, and that's our test data. So what we want to do is we want to avoid overfitting. So if we create an algorithm that works perfectly on our training data, it probably doesn't do very well on new examples. So it's like a fine balance between sort of generalization and accuracy is sort of the two things that we're going to balance here. Okay. Well, let's actually first load the data into Python before we go into our algorithm. Okay, so here's our fancy script. I'm going to put this somewhere online for you to take a look at it. I didn't have time to do it before this presentation, sorry. Let's import the libraries we're going to use, some basic libraries, and then TensorFlow, our backend, then Keras, the higher level library. This CIFAR dataset, it comes sort of package within Keras. So we can just load it from there. And here what I'm doing some preliminary transformations on the data. So here I'm just discarding all the parts that are not cats or ships and transforming the labels into a binary matrix. And then I'm normalizing the data to be between 0 and 1. It's easier for the functions that we're going to use. So we end up with 5,000 cat images, 5,000 ship images, labels for them, 1,000 cat images in our test data, 1,000 ship images in our test data, and the labels for those. And I guess we can take a look at one of our images, just for fun here, since we've got time. Okay, here's a cat. It's 32 times 32 pixels, so yeah, but you can still sort of say it's a cat. Okay, and then we're going to choose our algorithm, and we're going to use a convolutional neural network, which are sort of the state-of-the-art. It's sort of like a state-of-the-art model family for image classification these days. Actually, back when I studied machine learning about 10 years ago, neural networks were not in fashion at all. I was mostly taught that they are overfitted regression and they have no future. You don't need to study that at all. Turns out that was not true at all. Neural networks are nowadays very powerful thanks to some advances in algorithms and also advances in hardware, especially GPUs. And many of the best performing machine learning systems nowadays are very much based on neural networks, and especially these kinds of deep multi-layer neural networks. Here, just to fill the empty space in the slide, is an image of well, maybe the most famous convolutional neural network, the LeNet from 1998. Ours will be slightly more simple than this one. Before we go into our final model, just wanted to show you a couple of examples of different kinds of neural networks. Here is maybe the most simple neural network, the perceptron, fancily named. This is from the 60s. And it's, well, here's the whole classifier in one equation. But if we go through what it does, we have so the sort of basic building blocks of neural networks. We have layers. Sorry for everyone who's watching this on stream. I'm now pointing at the screen with my hands. But here on the left, we have an input layer, and on the right, an output layer. And each layer has neurons, which are basically just functions. And they are connected to each other. And each connection has an associated parameter called weight or W. So the input layer is just all of our input values for one training data example. So this could, for example, be all the pixels in our image or the pixel values we saw in the matrices. And what the perceptron does, it takes each of the values, it multiplies it with an associated weight, W. Then we just sum all the products. And then if that weighted sum is positive, our output layer neuron outputs 1. And if the sum is negative or 0, we output 0. So what this does, or how we could use this as a cat ship classifier, is that if the weighted sum is positive, it outputs 1, we say it's a cat image. If it outputs 0, we say it's not a cat image. So it's a binary classifier. And how we make the perceptron perform in different situations is by learning different values for this set of weights. So the only thing that changes between different perceptrons is what kinds of weight we got here. So if we wanted to use the perceptron for classifying our cat images, we'd learn some values for the W's using the perceptron algorithm, and then input our new images, and then it would output a binary value depending on whether it's a cat or a sheep. Except we're not going to use the perceptron because it doesn't work very well. It's a very simple model. It's famously bad on image data. It was an embarrassment to everyone when they realized that. So we are going to use a multi-layer neural network. Question? Yes, this only works if data is linearly separable in fancy math terms. And we, and for that kind of data sets, we often have faster and easier algorithms. So we're going to use a multi-layer neural network. This is also called a multi-layer perceptron. And if someone talks about deep learning, then they are talking about multi-layer neural networks. Here again, and I'm again pointing at the screen with my hands, sorry. We have the input layer again. So here we just input our data. So each X is, again, maybe a pixel value in our image. And then again, we have a hidden layer now. So we take all of our input values, we multiply them with weights, and then we feed them into our neurons in the hidden layer. And what the neuron does, it's actually just a function. So each each neuron takes as an input the weighted sum of some of our input x's, and then it outputs some function of the weighted sum. Often this is some simple nonlinear function like a hyperbolic tangent or a sigmoid function. We'll see some examples later on. And then we can use the output values of this hidden layer as input values in a different layer. And then we can stack these layers on top of each other until we've got something that works. Here in this example, we only got 3 layers. So one input layer, then one hidden layer, and then one output layer. And this output layer takes as input the weighted sums of the neurons in the previous layer, and then it outputs some value. It could here, for example, be the probability whether this is a cat or a sheep. So the things that we have to define in advance when we are choosing a model is basically these activation functions, and then how many layers and neurons we've got. And what we are going to learn is, again, just these weights. So we can use the same neural network for different classification tasks if we learn new weights for each task. And to do that, in addition to the activation function, we also need an error function. So some function that tells us how well this network performs classification. So when we have, for example, our test data, we know what the actual label is, and we can compute the label that the network gives, and then our error function tells us how well it did. And we're going to need that in teaching the network. Here, I'm going to go through this very quickly, because going through this in detail would take a lot of time, is the model of our cat-SNP network. This comes in 2 slides. Here's the first 4 layers of the network. So we have a convolutional neural network here. Often we have, well, this is like the basic structure for a convolutional neural network. Many of those, like if you use like a sort of actual facial recognition system or something, it has many of these sort of layers. But we're only going to have one because we want to be able to fit this in a very short time. Input here is going to be the three matrices that we saw before. So the green, red, and blue pixel values for our image. And what we're going to do is we have a convolution layer. So this is a very hand-wavy explanation. We take small matrices or small sub-matrices of our image matrix, and then we multiply them with what's called a kernel matrix, so small matrix, and then we stack those matrices into new matrices. And those kernel matrices are one of the parameters that we're going to learn here. So what this part does is we're sort of trying to find sort of small localized features in our image. So for example, we want to recognize cat ears and cat eyes and sheep. I don't know what are sheep features. Maybe sharp angles could be something that we have in sheep but not in cats. And then to reduce dimensionality, because there's a lot of data here, we are just going to sort of subsample it into smaller matrices. So we take again small submatrices from these matrices and just take the maximum value from there. We lose some spatial definition there, but it doesn't matter because we don't want to know where the cat is. We just want to know there is a cat. And then we just flatten our three matrices into one big vector. And I didn't tell you what this is. This is the activation function in the convolution layer. It's what's called a rectified linear unit. It's a very common activation function in these sort of networks. If you didn't understand anything I said, don't worry. This was very sort of quick and inaccurate overview. But what we're doing here is we are sort of recognizing small local features that are somehow useful in recognizing whether we have a cat or a sheep. And then we're also reducing dimensionality so that we have fewer parameters in our classification layer. So what we do with the flattened vector, we have then what's called a fully connected layer. So we have a lot of neurons. I think we can take a look at the number. I think it was 128 neurons here. And each of the values in this vector connects to each of the neurons in this fully connected layer. So we have a lot of parameters here, about 1 million parameters. And here's the activation function. Again, it's what's called a sigmoid function, a very commonly used one. And then from this fully connected layer, we map to the output layer. We use what's called a softmax function, which pretty much just normalizes these input values into being probabilities. So what we have in the end is a probability of our image being a cat and the probability of our image being a sheep. So we input a color photo, and then our network spits out two probabilities, the probability of catness and probability of sheepness. They of course sum to 1, so we don't need both of those probabilities, but if we had, for example, 3 different classes, we could just add a third label there. Okay, let's now see how this looks like in code. Again, back when I studied, that wasn't that many years ago, but we didn't really have these sort of high-level libraries back then, so I remember that it was a lot of handiwork, a lot of chain rule of derivation when you wanted to implement these models. But now we have Keras, where you can just define this model and just call add and add all sorts of layers here, and it magically works and it does all the optimization and everything for you. So here's our model. It's sequential. So we have only connections from one layer to a new layer, so we don't have, for example, connections within a layer. Here's the convolution layer, so we have 3 times 3 convolutions there. Our activation function is the rectified linear unit. Then we have the pooling layer. The dropout parameter means that when we are teaching the model, we are each time not using 25% of our connections to avoid overfitting. And here's the fully connected layer. First the flattening. Then we have 128 neurons with sigmoid activation functions, again some dropout. And then we have 2 softmax neurons that output probability. And I don't really have to know anything about the math. I can just write this down and it'll magically work. Oops, here. Let's now, since we've got time, take a quick look at the model. So here's just a summary on the screen. So one thing that's interesting is the number of parameters. Here's, for example, the convolution layer, about 900 parameters. And then there's the fully connected layer, which has more than 1 million parameters. So these are the W's that we're going to learn. So in next step, we're going to use the training images, the CIFAR dataset, and learn actual values for the 1 million parameters that we just saw there. And we're going to use backpropagation, which is the standard way of learning in these sorts of feed-forward neural networks. I am not going to go very deep into it. This is very, very, very hand-wavy, non-mathematical, non-technical overview of how you do these things. Start with some random weights. So we initialize the network with some random weights, whatever. Then we take some of our training examples. I think I used 50 here. And then we compute classes for them with those random weights. It's not going to be a very good result. And then we use those classification results and actual values and the error function to get the gradient of the error function with regard to the weights. And then in the parameter space, we move the weights a tiny bit towards the direction of the gradient. And then we do this again with these new weights for some new training examples. And then we repeat this until the results are somehow good enough for us. This sounds like a lot of work, and it sure is. Our model is such a simple one that it's fitting it is going to take a minute or so. But large, like commercial level neural networks can train for weeks on large GPU farms. And of course, nothing guarantees that we will get a good solution. We will end up in some local optimum somewhere. I mean, if we have 1 million parameters, then we are optimizing on an error surface in a 1 million dimensional space. It's a hard thing to get a good solution there. There are, of course, many methods and tricks for making learning faster and better and getting better solutions, but we're not going to go into that. Okay, here let's now fit the model. So here I'm just choosing the optimizer. This RMS prop is a it's a type of gradient descent. If you that's sort of adapted for neural networks. Here we are choosing our error function. So the categorical cross entropy, again, very much something that's commonly used in these kind of classification tasks. And here I'm just saying that I wanted to output the accuracy as it's optimizing. And this model.fit then does the hard work, the training. And most of these parameters are just pulled out of my hat. Like why is the batch size 50? Why do we use 50 examples at a time? Well, I just had to select a number, so I selected 50. So there's room for optimization there. Oops. I forgot to copy paste something, probably this one. Then let's try to fit the model. Okay, now we are running backpropagation. And you can see here this AC here is the accuracy, so how well the model is doing on training data, and the number should sort of keep getting bigger as it is. So we are moving hopefully towards some good set of W's. And now we're done. Now we have trained a neural network. Thank you. And now we can use it to classify images. So here are the cat and the sheep from before. I've cropped them or scaled them down to 32 times 32 pixels because that's the size that our network expects. And we can see how well our network does on these two fine examples. And these are not part of the CIFAR dataset. These are just random images from the internet. So we have not used these images in training or testing the model. So, okay, let's first take a look at how well our model performs, actually. So here on the bottom of the screen is accuracy on test data. So how well our model performs. Our accuracy is about 90%, so that means about 90%, it classifies about 90% of the images correctly. And then of course we can ask, is this a good number or not? And the answer is sort of. This is a tiny network. We didn't have a lot of data. All these parameters that I chose, I haven't optimized in any way. So I think this works pretty well for such a small example. But with some tuning, this would probably work a lot better. I mean, best of these convolutional neural network classifiers work eerily well. So with some tuning, we'd probably get a lot closer to 100 here. Okay, then let's see how we do on our cat and on our sheep. So I'm reading here the images in, then converting them into NumPy arrays, and then printing the accuracy. Here's the cat again. So the cat here. So this first number is the probability of it being a sheep, and the second is the probability of it being a cat. So our algorithm is about 80% sure that the cat is a cat. And then for the sheep, it's, well, practically 100% certain that the image is a sheep. Yeah. And what else? I also added a completely new type of image here. So we have a potted plant. I think this was some sort of a fern or something. And let's see what our network thinks it is. Yeah, how many guess cat and sheep? Why? Yeah, and then our algorithm thinks it's probably a cat. So it's about as certain of its catness than it's of the actual cat. So if this worked really well, of course we'd get about like a 50-50 probability here that it would show that it's uncertain of the label of this image, but it doesn't really work that well in that way. And this sort of just to show that this classifier of course does not generalize into anything else than the tasks that we trained it for. There a question? Okay, so for anyone listening in the stream, the question was, can we sort of, what does it mean that the cat and the a plant gets some similar probabilities. Well, and my answer is yes and no. So yes, that means that the plant picture has more these sort of local features that are cat-like. So maybe less sharp angles and more this sort of, I don't know, that kind of variation that cat pictures have. But one of the problems with neural network is that, yeah, the model that we fit it's the million weights. So we got a million real values, and understanding what they do is really hard. So one of the problems and challenges with neural networks is understanding why they make the decisions they do. Some different types of machine learning models, different types of model families often produce results that are easier to interpret. But here the network outputs something, it's pretty much a black box. We could, something that we could do, probably let's not do it now, we don't have that much time. In these sort of cases, we can take a look at the kernel matrices that we have in the convolution layer, and they sometimes tell us the interesting details, but often, and in general, it's very hard to interpret why the network does what it does. Yeah, and I guess, and what we skipped, a lot of things, there are many different types of neural networks, and we didn't really go very deep into the model and how to train it, and so on and so on and so on, but this is how you implement AI in 30 minutes. Any questions? There. Question was, do we get better results if we have larger images? Probably yes, those are really small. That if we had larger images, we'd have more parameters, and in training the model would take a lot longer. So that's why I chose these very small images. But yes, certainly larger images would probably work better. Yep. So the question was, does this work on black and white pictures? Well, the here, no, because the network expects to get these sort of three matrices, so the green, blue, and red matrices. So like the dimensionality of the input data is wrong. But we could, of course, train this on black and white images perfectly well, and it probably work all right. Question there? Yeah, of course we could just use the black and white matrix 3 times. Yeah. If the network has learned to use color information in classification, then the black and white images probably wouldn't work that well, but it's hard to say without trying. But if we suddenly had a bunch of black and white pictures, it would probably be better to then train a new network. Okay, if there are no more questions, then thanks for listening, and I'll try to put these slides and the code online so you can run this yourself if you want. Thanks.